So hi guys, in this video we would be talking about cross validation and data mismatch. We would be also looking at what is basically the no free lunch theorem, because it is a very nice theorem which is being implemented in other some real world problems. So yeah, directly starting up with what we talked about in the last video was holdout validation. We usually split the data training set into training and validation step. Then we used a number of models, suppose n number of models, and in these n number of models, whichever model performed the best on validation data after being trained on the training data that we split it from the main training set, we would be choosing the best model from which the metrics have been computed. So what is the problem in that part? So as I told you, since the final model will be trained on a much smaller training set, it would be like selecting the fastest sprinter to participate in a marathon. And this solution usually works quite well. However, if the validation set is too small, then model evaluation will be imprecise, and you may end up selecting a suboptimal model by selecting others model and all. So what we can do here? We can perform repeated cross validation using repeated many small validation sets. I have already talked about cross validation, how it works and all. So I would just directly come to the implementation part. Since we can perform a number of repeated cross validation using repeated many small validation, each model is evaluated per validation set. You can see here, this is the testing data, and this is the training data. Now on that, iterations have been performed, the iteration 1, iteration 2, and all the data that has been consisted in this, and key iterations have been performed. I told you we would be performing repeated cross validations, and each model is evaluated once per validation. So you can imagine like this. Yeah. So this is the training set, and this is the whole data. This is the whole data, and this is training part, and this is testing part. Yeah, this is testing part for now. So each model is evaluated once per validation set. Now suppose this was split it into two part. I told you, training and validation. Now the every model that is being made, this is the model 1. This is being evaluated only once per validation set, and after it is trained on the rest of the data by averaging out all the evaluations. Suppose these are the models, all the evaluations of a model, we get a much more accurate measure of its performance. So suppose there were six number of evaluations that has been done, so we would find out the average between all the models. We will find the average, that what is the average of these six evaluations. Suppose the model 1 is giving you an accuracy of suppose 75%, and model 2 is giving 82%. Now there is a chance that model 1 is giving you 93% accuracy on first part, first evaluation, but on second and third evaluation it is giving only 31 and 72. Hence it we would take the average of the whole part to make sure that by averaging out all the evaluations of a model, we get a much more accurate measure of its performance. Hence this is how cross validation would come into play. Now, let's talk about yet another part, that is data mismatch. So, in some cases, it is easy to get a large amount of data for training, but it is not perfectly representative of the data that will be used in the production. I told you in two videos back that both should contain all representative types. It should not be like you are giving you have got a data set like this that consists of 10K images. Now, yeah, and we have splitted the data in like this. This is the training part, this is the testing part, and we give 5K image to this and 5K image to this. Now what is the point here? Now suppose there was a image, this is just consider it a image classification data set. So this was an image of a dog, and this was another image of a dog from another angle. Now suppose both of these images is given to this model or is given to this model, it would cost double to the model, because for training set it has seen both the images, but it would not get tested on. You cannot see how it is performing. Same implies for the testing part. You have given it the images to the testing part, but you haven't trained the model on that part. So how would the model get to know that there is also a dog in the whole data set? Hence both models should contain, or the both data should contain all representative data types. We need to make sure no duplicates or near duplicates end up in both set. So this is something that we should make sure of, that while data mismatch. So in some cases, as I told you, you can easily download millions of pictures of flowers. You have got a data set like this, and it has 1 million pictures, suppose 10 million pictures of flowers. Okay, I would just, yeah, you can easily download around 10 million images of the data sets of flowers on the web, but they won't perfectly represent of the pictures that will actually be taking using the app on a mobile device. Perhaps you only have only 10,000 representative pictures, because these 10 million pictures are not all different. There are must be some duplicates to make sure training part and testing part both are being done in a mannered way. So after training your model on the web pictures, if you observe that the performance of your model on the validation set is disappointing, you will not know whether this is because of your model as overfitting the training set, or whether this is just due to mismatch between the web pictures and the mobile app pictures. One solution that is being called by Andrew Ng. If you don't know about Andrew Ng, I guess you should know. He is like a god of data science and machine learning. Even I have learned from him. So yeah, we would keep a train dev data set, a train dev data set. I would just show you directly. Yeah, so the train dev data set, for these are the point of error. Means before coming to train dev error, I would just like to talk about what is basically train dev data set. So after the model is being trained, you can evaluate on the train dev set. If it performs well, then the data is not overfitting the training set, so it performs poorly on the validation set. So what we do is, after the model is being trained, you have evaluated on the train dev set. How does train dev set works? So train dev set works like this. This is particularly compiling the making sure that errors between the problem. Yeah, this is the training error that you are getting, this is the training dev error you are getting, and this is the dev error. You must read development error, that is being part, huh. So this is the variance problem between the both the sets, and this is the data mismatch problem, which is the major reason for many times performing the algorithms and model compiling. So what we do, you can try tackling this problem by pre-processing the web images to make them look like the pictures that can be taken by the phone app. Because it's possible that you have given a web image to your a phone app, Android application that is using machine learning, and you have trained a model on images like this. This is a flower, and this is a very nice picture of flowers, but the pixel quality that has been taken by phone and the environment that has been taken by phone is not very similar. Hence we should definitely test it on the train development set to make sure that it is performing good on even the development part. So yeah, we have talked about all the parts of the main challenges in machine learning. One more part I would like to talk about is no free lunch theorem. No free lunch theorem. Yeah, so this is a very big theorem, but I would just like to say 2 to 3 lines about that. So what basically this theorem says is, no free lunch theorem, that no algorithm is the best. No universally best algorithm exists in on our planet. A model is a simplified version of the observations. What we are basically doing, we are giving it a number of observations, and the model is giving us a simplified view of that. The simplifications are meant to discard the superficial details that are unlikely to generalize to new instances. Hence, however, to decide what data to keep and what to discard, you must make assumptions. Hence, it is proved that no model in this world is the best. And it's obvious. If you are studying ML and data science from a long time, you must have got an idea that no model in this world can be perfect, because it's not even possible. All the data sets that you're evaluating, all the things that you're doing are on the basis of assumptions. Hence assumptions can't always be correct. Hence we keep changing and improving our models to make it near perfect but not perfect. Hence this is it for the video. Thank you and have a nice day.